Arduino inverter with joystick. Hello friends, it's an Arduino engineer. This video has a good application topic. Controlling the rotation of a powerful three-phase motor from an analog joystick using Arduino. Both the speed of rotation and the direction of the motor are controlled. We tilt the joystick handle in one direction. The motor rotates forward. We tilt it in the other direction. The motor rotates backward. The rotation speed is controlled by the amount of inclination of the joystick handle. This is a complete analysis of the project as you like, with a diagram and a program, so it will be interesting. To implement this project, we have an analog 2D joystick. It consists of two variable resistors with a resistance of 5 ohm. We will use only one axis of the joystick, only one of its resistors. If you don't have an analog joystick but want to repeat the project, you can replace it with a simple variable resistor. We also need a single-phase variable frequency drive inverter. It is single-phase but is designed to control three-phase motors. It has an analog input 0 to 10 volts to control the speed of the motor. The inverter also has discrete inputs stop, run, and reverse with galvanic isolation. They respond to the GND signal. It also has two output voltages for powering external control devices. A 12 volts output from which you can power the Arduino, and a weak 10 volts output that has a significant current limit of 30 milliamperes. The scheme of the inverter control device from the joystick is as follows. At the core is the Arduino Nano controller. A joystick in the form of a variable resistor is connected to the analog input A0. The analog output signal is generated using a PWM signal at a discrete output D9. Further, the PWM signal is smoothed by an RC filter and amplified by the LM358 operational amplifier. At the output of the amplifier, we get an analog signal of 0 to 10 volts, which is directly proportional to the level of the PWM signal. Discrete inverter control outputs are formed using two N3904 bipolar transistors. When a logical unit is supplied from the controller pin to the base of the transistor, it closes the GND signal to the input of the inverter. In this case, the LED of the optocoupler inside the inverter is activated. The power for the control circuit is taken from the 12 volts output of the inverter. I first tried to power the operational amplifier from the 10 volts output of the inverter, but as you will see later in the video, this was not enough. So the op-amp was powered by 12 volts as a result. But the desired range of 0 to 10 volts is formed at the output. From 12 volts to 5 volts, the voltage drops using a switching regulator based on the LM2596. The device is assembled on a circuit board. On the one hand, there is a screw terminal block for connecting a joystick, and on the other, for connecting to an inverter. The program to upload to the Arduino Nano looks like this. First comes the declaration of constants that store the Arduino pin numbers. The next two variables are responsible for determining the average position of the joystick. Push forward sets the analog input value after which the motor should start moving forward. Pushback sets the analog input value below which the motor should rotate backward. It turns out that from the analog input A0, depending on the position of the joystick knob, a value comes in the range 0-10-24. In this case, in the range 600-1024, we consider the movement of the motor forward, and 0 to 420 backward. And the range 420 to 600 is considered the middle neutral position of the joystick. In this range, the motor must stand still. In the setup function, we define 4 discrete Arduino pins as discrete outputs. It also defines a UART port for diagnostic messages. In the main loop of the program, the value of the analog input A0 to which the joystick is connected is first read. Here we get a value in the range 0-10-24, and further in the program, all actions are based on this value. If it is greater than the specified 600, then the stop and reverse signals are turned off and run is turned on. A PWM signal is also generated in the range 0 to 254 according to the input upper range of the analog signal 600-1024. If the joystick is turned in the opposite direction, and the value of the signal on pin A0 drops below 420, then the output discrete signal stop is deactivated, and the reverse and run signals are activated. A PWM signal, 0 to 254, is also formed in inverse proportion to the lower range of the input signal. The value 419 of the input signal from the joystick corresponds to 0 PWM signal at the output, and vice versa, 0 signal at the input corresponds to a maximum of 254 PWM signals at the output. And if there is a value at the analog input that is in the middle range of 420 to 600, which corresponds to the neutral position of the joystick, then the run and reverse signals are deactivated. The stop signal is active, and the PWM output is 0. The motor is stopped. The next step in the program is sending diagnostic messages to the port monitor. This is useful when debugging a device. Two parameters are displayed: the value of the analog input, that is, the position of the joystick, and the value of the PWM signal at the output. A delay of 100 milliseconds is also inserted in this loop. Here, when debugging the analog output to control the inverter on a voltmeter, it can be seen that when the operational amplifier is powered from a voltage of 10 volts, the output voltage is not enough. We need 10 volts, but in fact we get 0 to 8.7 volts. But when powered from 12 volts, the result is a full voltage range at the output of 0 to 10 volts. Here, a careful debugging of the device is already underway, with the inverter and motor connected. And here is a demonstration of a working project. By pressing the joystick in one direction, you can smoothly control the speed of rotation of the motor in one direction, and when you press it in the other direction, you can smoothly control the rotation in the opposite direction. Such a design will be useful in many applications of three-phase motors. A very convenient solution for reverse control. As a suggestion for improving the device, we can suggest using a controller with a more accurate analog input and PWM output. That is, with a greater capacity. This will help make smoother and more sensitive motor speed control. If you like the video, support it. Subscribe to the Arduino Engineer channel, like and share it with your friends. The link to the text version of the project is under the video. Thank you for your attention. See you again soon.